Call on the first speaker, Nicole. I see you have 25 slides for a 25-minute talk, so that should go well, but if it doesn't, I'll try to let you know somehow. And people who aren't talking should mute. I will mute.
Sorry, I think I started my video before muting. Can you hear me?
Yes, we can hear and see you.
Cool. And I'm about to share my slides. Can you see them?
Yes, very good.
Cool. So today I'm going to be talking. Can you also see the Zoom people in the side, or is that not sharing?
The Zoom people on the side?
No, it's this. Everyone has his own panel,
Okay.
so I think you're fine. Okay.
Perfect.
Yeah,
Thank
everything
you.
looks good for me. Yeah.
Okay, so today I'm going to be talking about an application of tracking in the context of flavor tagging. So the motivation is that we're interested in identifying B-jets because of the predominant branching ratio of Higgs to BB bar. And so what we mean by that is that since the behedron has a characteristic long lifetime, the experimental signature in the detector is a displaced decay and a set of displaced tracks. So how we organize B tagging on Atlas is through a hierarchical organization of both low-level taggers and high-level taggers. And today I'm going to be focusing on low-level IP-based taggers. So what this means is we utilize the collection of tracks to make a B tagging classification decision, although we also have vertexing-based algorithms, which we then combine together into another high-level discriminant, which we call DL1 or DL1R. So I'm going to talk about today our first off IP-based taggers that we're using, and then the new model that I'm introducing and its performance, and then finally an investigation into what the model has learned. So I'm going to be start off sharing which are the current IP-based taggers that we're using in Atlas and their limitations and the introduction of using a deep sets architecture to solve the same problem. So some of the key features for identifying displaced tracks are the significances or the impact parameters divided by their resolutions. And for flavor tagging, the signage of the impact parameter is determined by the projection of the IP along the jet axis as illustrated in the graphic on the right side of the slide. If it's consistent with being from a true long-lived particle, this means the projection along the jet axis will be positive and the IP sign will be positive. Otherwise, the IP signage is negative, and this is illustrated by the two significance distributions in the lower left-hand figure, with SD0 on the left and SD0 on the right. And the key takeaway is that this lifetime signage means you have an asymmetry for the tracks that have a true heavy flavor hadron, as shown in the more positive significance distributions for tracks in C and B jets than in light jets. So the first tagger that we have that takes advantage of these significances is called IP3D. What it does is it takes these significances and builds up a 2D probability distribution for each of the jet flavors. And then it assumes that the individual tracks in the jet are independent of each other to build up higher level discriminants by taking the ratio of the probabilities and then the product over them to build up either a discriminant for B versus light in the left-hand equation or B versus C in the right-hand equation. And also, since these resolutions are dependent on the hit category, the hit patterns of the tracks, these PDFs are derived for 14 different categories defined by whether or not the track has hits in the innermost layers, etc. Some of the cons of why we're looking for something else is that track independence is firstly an overly simplistic assumption. And also whenever you have a histogram-based approach, this isn't going to scale up to multiple variables. And this is just to elaborate a little bit more on this point that the tracks are correlated and assuming uncorrelation is overly simplistic. This is plotting the leading SD0 track in the jet versus the subleading or second highest SD0 track for B jets on the left and light jets on the right. And you can see that since you have a high multiplicity of tracks with large IPs in B jets, the correlation is positive. So this independent track assumption is overly simplistic. So the algorithm that we have currently adopted to combat this is RNNIP. So it takes account to account the correlations between the tracks by using the recurrent neural network architecture. What this means is for each track in the jet, you process it with a neural network that keeps track of a fixed dimensional hidden state while iterating through the tracks in the sequence before going to a classification decision. And in addition to taking care of the correlations, it also avoids the cursive dimensionality inherent in histogram-based approaches. So this allows us to, instead of needing 14 exclusive categories, just adding in the low-level hit information explicitly, the low-level hits, and then also incorporating the kinematics of the decay, such as PT frac, or the ratio of the PT of the track divided by the PT of the jet, or the opening angle between the track and the jet axis. So the reason why we're still looking for something new is, first off, with this sequence model of the jet, there really isn't a clear ordering for the sequence. As you can see in the graphic, it says these tracks with the currently adopted RNNIP are ordered by SD0, but this is an empirically driven ordering choice, not dictated by the problem. And also for sequence-driven problems, this is going to scale based on the number of tracks that you have in the jet, so this makes both the training and evaluation time slower. But before introducing the new algorithm, I just wanted to show what we had gained with the RNN. And the way that we show performance in B-tagging is using ROC curves, where we combine the 3 output nodes into a single discriminant dB by taking the ratio of the signal, probability PB, divided by the 2 types of background, weighted by the FC, or charm fraction, to trade off light versus C jet rejection. And so the distribution of the discriminant is shown in this figure. For light, C, and B jets. And what we do is we set a threshold on this value, and B jets above this threshold define a signal efficiency. And then the mistag efficiency, or light and C jets that are also above this threshold, define the background rejection, which we define as 1 over the mistag efficiency. And then by scaling over this threshold value, this gives you a signal efficiency versus background rejection pairs that you can then plot against each other. So in slide 11, I'm showing such a ROC curve for the currently adopted Atlas taggers. And what I want to guide your eyes to are the green and blue lines on this plot, which is showing DL1, which is the high-level tagger without the RNN, and DL1R, which is the high-level tagger with the RNN. And you can see that including the RNN with these correlations and extra variables, we get an increase in performance, pretty good increase in performance in both light flavor jet rejection and C jet rejection. So the question is if we can find a similar algorithm that has a similar gain in performance while not having being susceptible to needing to order the jet like a sequence and have this empirically driven ordering choice. So the motivation is to instead model the jet using a set, using, for example, a permutation invariant algorithm. So the papers that I referenced up here are the original deep sets paper, and then the paper applying deep sets to a phenomenological quark versus gluon tagging problem. And so I'm using the same notation as the energy flow paper. So the algorithm is encoded by this equation, where the PI is the features for each of the tracks in the jet. And then we have a dedicated neural network phi, which extracts higher level track features for each track in the jet. Then the permutation invariance of the algorithm is encoded by this sum operation. And then the correlations between the tracks in the jet that were powerful for the RNN are now taken into account with the jet level network F. And this allows you to compute higher level observables denoted by O in this equation. So for the first comparison plots I'm going to show, the baseline algorithm is going to use the same inputs and track selections as RNNIP, which amounts to 13 features for each track in the jet. And then just to be a bit more concrete, slide 13 is showing the specific architecture that we used for implementing the neural networks phi and F in this equation. You can see the architecture with 3 layers, and the same neural network is applied across each track in the jet before concatenating. And then we sum over the jets along the track axis to give a 2-dimensional vector for the mini batch size and track latent space before processing the correlations in F, and the final observables are going to be the per class probabilities, PL, PC, and PB. Additionally, we found it helped the performance to include batch normalization between the layers. And the name for this tagger is DIPS, which is an acronym for Deep Impact Parameter Sets. And that's going to be how I'm going to be labeling the tables and legends in the next sections. So this brings me to the first experiments. This is evaluating the performance of DIPS. And first, I'm going to show you a comparison of the nominal RNNIP versus DIPS, and then the further optimization studies that we did with the DIPS algorithm. So one of the reasons why I was motivating that we were trying to find a replacement for the RNN was because recurrent neural networks are slow. So the first question is how these models compare in terms of timing. So for this, I'm looking at a training sample, which has 3 million jets for training and another 3 million jets for evaluation, both using TT-bar, and 20% of the training data set is held out as a validation set for early stopping. And the table below shows a comparison with RNNIP in the first row and DIPS in the second row. And the number of parameters is chosen such that they're roughly the same between the two models. You can see that in terms of training time per epoch on a GPU, the DIPS model is performing a factor of 3 faster than RNNIP. Additionally, we show the times for inference in the last 2 columns, both on a GPU and on a CPU. Here, looking at the time for evaluation on the whole 3 million set of test jets. And it's again a factor of 3 to 4 speed up in evaluation time as well. So it's doing better in terms of the training time. The next question is how it's performing in terms of the overall performance. So I'm showing the ROC curve metrics again on this slide, with the light rejection versus B efficiency in the left-hand plot and C rejection versus B efficiency in the right-hand plot. And so for these curves, higher rejections is a better tagger. And so you can see with the ratio with respect to RNNIP in the lower subpanel, the DIPS model is outperforming by a factor of 20% in terms of light rejection and up to 5% in terms of charm rejection. So the motivation for this is that since the ordering of the RNN was something like empirically driven, not motivated by the problem, this means DIPS is a more physically motivated model. It can make a better use of the trainable parameters that we have. So this is why we have the increase in performance using the same inputs that we had with RNNIP. So one of the reasons why we were excited about this faster turnaround time for training and model evaluation is it makes it faster to do, for example, R&D studies. So on this, on these 2 curves, I'm showing 2 additional optimization studies that were conducted. The purple line DIPS on this plot is exactly the same as the purple line on the previous plot. And the legend above shows the track selection used for this tagger, which is also used for RNNIP and IP3D. However, the cyan line shows if we loosen these track cuts, lowering the PT threshold and opening up the impact parameters. And you can see that the looser track selection helps DIPS perform even better. And then additionally, the orange line is showing the loose track selection combined with new inputs, namely the impact parameters D0 and Z0 sine beta for each track in the jet. And so this is a factor with respect to the nominal DIPS. This is a factor of 2 improvement for light rejection and 50% for C rejection. And then the last the last slide in this section is looking into how the performance, overall performance breaks down into different topological regions. Namely, looking into if you have a flat, if you define a flat working point in each bin, how the rejections evolve. So what this means is that in each either PT or ADA bin, we vary the threshold such that we fix the B-jet efficiency to be constant at a given working point. For these plots, it's chosen to be the 77% working point, and then we look at the evolution of the rejection. So the light rejection is given in the left-hand column and the charm rejection in the right-hand column, with the variation with respect to PT in the first row with respect to eta in the second row. And the takeaway message here is that the overall performance gains that we saw in the ROC curves are also reflected in performance gains in the individual regions as well. So then the last section that I'm going to cover today is an investigation of what the model has learned. So for this section, I'm going back to DIPS, which is trained with the nominal track selection and nominal variables, and I'm going to be investigating what the model has learned in terms of saliency maps, and then go on and see how this would impact our current workflow in combining with Atlas B tagging using our current existing calibration methods. So first off, to investigate what the model has learned, we're using a metric called a saliency map, and the reference from image classification is given on the top of the slide. But for this application problem, what we did is we took the B tagging discriminant, the equation in the lower right-hand section of the slide, and then the derivative of this discriminant with respect to the inputs by back propagating the result of DB through the network. And so this is the gradient equation on the upper right-hand part of the slide. So what this means is for a single jet image, we have a two-dimensional image given by the number of tracks by the number of track features. And this gradient gives us like a linearized view of the neural network, and it's a metric to tell us how to modify the inputs to, for example, make the jet more bee-like. So instead of looking at a single jet, I'm looking at an ensemble of jets. So for example, we're looking at B jets that failed the 77% working point, or the green histogram with the set of jets below this dashed line cut. And then also to take out the track multiplicity dependence, I'm just looking at jets that had exactly 8 tracks. And then additionally, for computing this average, the tracks are going to be sorted by SD0. So this is what this slide is showing. The lower, the rows are denoting the tracks in the jet sorted by SD0. So this means that the first column, or track 1, is the track with the largest SD0 value, whereas track 8 is the track with the smallest SD0 value. And then the corresponding rows of the image are showing the different track features. So the first thing that I'd like to guide your eyes to are the significance distributions in the lower 2 rows of the figure. And you can see that these gradients are positive and strong for up to the first 5 tracks in the jet. So this means that to make the jet more bee-like, you only want to increase the impact parameters for the first 5 tracks. Additionally, you can see that log delta R is also has a positive gradient. So this is telling us that it's learning about the correlations between having a displaced track and also having a large opening angle. And then finally, you can see the splash of pink in the upper left-hand portion of the figure. These variables are corresponding to whether or not the hits in the innermost IBL layer or the next 3 pixel layers are either shared or split. And so the fact that they're negative means that we want these tracks with the high significance values to also be good quality so that they're trustworthy for making a B tagging decision. So it was interesting to take the neural network trained just for classification and see what properties or characteristics of B hadrons that it had learned in the process. And then the final section that topic that I wanted to mention today is the impact of putting such a tagger into our existing workflow. So we train the taggers on Monte Carlo simulation, but then apply them to data. And to accommodate for this domain adaptation, we compute scale factors or ratios of the efficiency in data divided by the efficiency in Monte Carlo. And we do this for each of the jet flavors. So we need to isolate a pure sample for each jet flavor to do this. So it's easy to isolate B and C jets in TT bar, but it's more challenging to get a pure sample of light jets. And the reason why is because of these rejection curves that I showed before with these really large rejections. Order 1,000 means that as soon as you apply the tagger, specifically at the tighter working point, you're going to get a sample that's dominated by heavy flavor jets after tagging. So that means that each of the low-level taggers that we feed into the high-level tagger also has a flipped definition for this light jet scale factor calculation. So what I mean by a flipped tagger is a definition of the tagger that has a similar discriminant for light jets, but a drop in performance from B jets, so it won't be dominated by the heavy flavor contribution. So the key feature that we use here is the symmetry of the track impact parameters and significances in light jet, i.e. assuming that the track's significances are dominated by the resolution effects. You can see how justified this assumption is where I'm re-showing these significance distributions. And then for the flipped definition of the tagger dips, it uses the same neural net that was trained on the nominal track selection, but then when running in the flipped tagger mode, we modify the inputs, just the significances, by multiplying the impact parameters by -1. So this means it's going to make B jets look very different, because instead of having a lot of positive impact parameter significances, it's going to have a lot of negative ones. So that's a very different input distribution. But hopefully light jets will be more or less the same. So this is my last plot slide on slide 25. The upper two plots are showing the discriminant distributions for the nominal in the line histogram, or flipped in the filled-in histogram, with light jets given on the left and B jets given on the right. And so also the dashed gray lines on these plots are showing the delineation between the bins that we calibrate for the working points. And the takeaway message here is that the light jets are lying roughly on top of each other, while the B jet discriminant has a decrease in performance of the tagger in the upper right-hand portion of the plot. And so this is promising for plugging this into our existing calibration methods in a flipped definition of the high-level tagger. The final plot in the lower right-hand corner is just showing the cumulative density function when you're integrating from larger values of dB to smaller values of dB. And so the solid and dashed lines for dips and dip split for light jets in blue are roughly on top of each other, while you can see that the efficiency for B jets in the green lines has gone down a lot with the definition of the flip tagger. So in conclusion, what we showed today was that using set-based architectures, we introduced a new algorithm that avoids an empirically driven ordering choice of RNNIP, but also has substantial speed improvements. This is similar performance to RNNIP, which is already shown to be very powerful in Atlas official recommended taggers. But the factor of speed up in training time is a factor of 3, and further optimization studies give additional improvements. And then finally, I introduced a metric, saliency maps, which we've used to see that the neural network is learning properties that are consistent with what we're expecting from the hadron decays. So thank you very much for your attention and listening today.
Thank you. That was very nice and right on time. So we have time for some questions. So raise your hands on the Zoom, and you can clap with the little clap icon. So go ahead, Paolo Calafura.
Sorry, I don't have a video here. Hi, Nicole, this is Paolo Calafura. So I have a question on slide 15, sort of a technical question. Which kind of deep set implementation did you use? Yeah, this one.
What do you mean?
I mean, did you use one of the, well, there was a library which was posted after the paper came out at NIPS. Are you using that one?
So I used that for initial.
Library?
So I used the energy flow library for the initial studies, but then for the ones that I'm presenting today, we just did our own implementation in Keras to be able to put the batch normalization in. Okay, thanks. And the kind of on this slide, what kind of, so you have 50,000 parameters. So the memory footprint of this during evaluation is not that big. Or do you know what's the memory footprint of your selection? I'm sorry, I don't. Okay. I don't think I don't understand what it means.
I mean, if you need to load like 1 million parameters, you're gonna have maybe a gigabyte of memory used to load these parameters. But it looks like your parameter set is pretty small, right?
Yeah.
Okay. And yeah, the final question I have is this 46 seconds or 206 seconds are for how many events or jets?
Thanks, I should have specified that. So I did for 5 different independent trainings and then compared the training time per epoch for each of those 5 trainings. And this is the 3 million jets for training and then also 3 million jets for evaluation.
Okay, so it's pretty fast actually.
So maybe I don't see any other hands, but maybe I can ask a related question while we're on the slide. Why is it faster?
Okay, because for the recurrent neural network, you have to process each of the tracks one after another. So you have to process the second track, you have to wait for the first track to be done updating the hidden state.
So you can't do that in parallel.
Right.
Okay. Any other raised hands? I think we still have a minute, so I can ask another question. So what about calibration? So you're now exploiting properties of jets. So obviously your training samples, et cetera, have to get those right, those correlations and everything. Otherwise, it's now a liability. Also, right? The advantage becomes a liability if your simulation is not as good as you thought it was. So is any special considerations for calibration?
So that's why for the flip tagger, we needed this kind of definition, which is something that we also had to think through for the light jets as well in RNNIP. But actually, we just finished calibrating DL1R, and these are the scale factors for B jets, light, and C jets, and it works exactly the same for the calibration when you have the recurrent neural network included as well for an input.
So this is all data-based calibration.
These are all data-based calibrations. They're public plots linked from the
Okay.
link in the slide.
Good. More questions? Okay, I don't see any.